name is Maarten,
And I'm Carola.
and welcome to the latest entry into our series of computational geometry concept videos, in which we take a geometric concept and we dive into its history, definition, computation, and other interesting properties.
And today's concept is range queries.
Actually, maybe we can have some dinner first. I'm getting kind of hungry.
Oh, sure. Okay, what would you like?
How about some gumbo?
Yeah, that'd be great. Let's cook some gumbo.
Right, let's do it. If there's one single dish which exemplifies New Orleans food tradition, it's got to be gumbo, which is named after the gumbo plant, which is the African name for what's known in English as okra. Now, there are countless gumbo recipes out there which evolved through the centuries among the many different Creole and Cajun communities that live in and around the city of New Orleans. And in fact, there are magazines full of just gumbo recipes, which have pages among pages of recipes. And if you search for gumbo on most websites with recipes, then you will also find pages and pages of results. So, which recipe should I use? There are too many to try, and actually even too many to read through all of them. But there are some things I know about how I like my gumbo. So, for instance, I like it when the roux is on the oily side, so it doesn't have too much flour. Although, of course, it shouldn't be too oily either. And, well, let's see. I guess I want one which takes, well, between 1.5 and 2 hours to make. So, well, maybe what I want is just to find only those recipes which satisfy these two constraints, and then I can look through them and see which one I like best. But how can we do that? If we have a database full of gumbo recipes, how do we find exactly those recipes which satisfy our two constraints?
We can actually use geometry to answer this question because the two constraints are numerical values: the amount of flour used in the recipe and the total cooking time. In fact, we can represent every recipe in two-dimensional Euclidean space. But this is not the space we're living in. It's an abstract space where one dimension is the flour and the other dimension is the cooking time. So we have the set S of n sites which live in two-dimensional Euclidean space, so in an R2. Of course, in our example here, we only have 2 dimensions, but this can work for more dimensions as well. So if we were interested in filtering out the acidity of the okra, we could have a third okra dimension. Or if we're interested in the spiciness of the andouille sausage, we could have a 4th andouille spiciness dimension, which means then our sites would live in 4-dimensional space. All right, but now the set S is only part of our input. We also have a range R, and we're interested to see which sites of S lie inside the range R. So in the case of a 2-dimensional space, the range R is actually a rectangle. It specifies for the x-coordinate, meaning the flour coordinate, an interval where all the points that we're interested in have to lie in, and it specifies another interval for the y or cooking time coordinate that the points have to lie in. We're now ready to define a range query. Given a set of n sites and a range R, which of the sites in S lie inside R? In other words, the output of this range query is the intersection between S and R.
One way of solving a query like this is by just going through the data, so going through all the sites in S one by one and simply verifying for every site whether it lies inside the range or not. So that is an algorithm, and even better, it's an algorithm which only takes linear time. So that's the best we can hope for, right? Well, if we wanted to do this only once, then yes, this is the best we can hope for, because we'll have to look at every site at least once to see if it lies inside R or not. However, or what if I wanted to host a website which has all the Gumbo recipes and which allows millions of users to find their favorite Gumbo recipes, each within their own desired rectangle? Well, in that case, it turns out that we can do even better than linear time. We can store the sites in S in a clever way, such that when we're given a query range, we can find all of the sites inside that range without the need to look at all of the sites in S. So such a way of storing the sites is called a data structure. And actually there are many different data structures which support all kinds of different queries. So the range query is one possibility, but there are other queries. For example, we also have a video about point location queries. If you're interested, you can click right here. There's actually a whole range of range queries, because you can have different shapes of ranges.
Right. So, for example, you could have a circle as a range, and in fact, in 1951, Evelyn Fix and Joseph Hodges looked at a circular range query. But that was in the context of classification problem, which is, important in machine learning.
Machine learning, yeah. AI. Yes, if the ranges are rectangles, then we also call this problem orthogonal range searching. This shows up in the context of databases in the early 60s.
Yes, in the 60s already, and in fact in 1970, this formed the basis for the notion of relational databases.
Edgar Codd.
Oh, by Edgar Codd, yes, exactly. Edgar Codd, invented the relational database,
which is still the mathematical foundation of the databases that we use every day, every second of our lives. Range searching was mentioned as a data structure problem for the first time by Donald Knuth in his famous Art of Computer Programming in 1969.
Right, but in 1975, John Bentley invented the KD tree,
right.
And
fascinating things, KD trees. But what's the dinner time?
Let's take a closer look at one of these solutions. A KD tree is a hierarchical subdivision of the k-dimensional Euclidean space. In our case, it's actually a 2D tree and subdivides the Euclidean plane. So how does this work? Well, we start by drawing a vertical line that has half of the sides of S to its left and the other half to the right. So in this case here, we have a total of 16 sides. And this line over here has 8 sides to the left and 8 sides to the right. And then for each half, we draw a horizontal line that has half of those sides, meaning a quarter of the total above it, and half, meaning a quarter of the total below it. And then for each resulting region, we draw again a vertical line that has half of the sides to the left and half to the right. And we continue doing this until there's only one side left in each cell. So why is this called a tree? Well, the word tree here is really different from the kind of tree we've used before in our minimum spanning tree video, for example. It's really, in our case, it's really a tree on the subdivided regions of the plane. Mathematicians just really love trees. In fact, we can visualize this tree as a bunch of connected nodes that represent rectangular regions of the plane. So this line divides our plane into a left part and a right part. Now on the left side, we have this horizontal line that subdivides our sites. And on the right side, we have this horizontal line which subdivides our sites. And now in the next regions, we again have vertical subdividing lines. Now L2 and L3 subdivided their regions into regions above and below those lines, while L4, L5, L6, L7 again subdivide their regions into left and right of their lines. And the next set of lines again subdivides their regions horizontally.
So now what we can do with this KD tree is answer questions about our dataset S. So for example, a simple question could be, I have a query point Q and I want to know whether Q is in S or not. So to answer a question like this, if we have a KD tree, we don't have to look at all the sites, but we can instead go down the tree and ask a question about our query point at each level in the tree. In this case, the first question would be, am I left or right of L1? And well, it turns out my query point is to the right of L1, so I go down the right branch of this tree. And then the next question would be, am I above or below L3? Well, Q is above L3, so I follow the above path in the tree. Then the next question is, am I left or right of L6? Well, the point is left of L6, so I go to the left in this tree. And the next question is, am I above or below L12? Well, the point is below L12, so I go to the below path in the tree. So depending on the answer at every node in the tree, we follow a different path down this tree and we end up at a different site. So in this case, the tree points us to this particular site, which corresponds with this site in the plane. And now I only have to test whether my query point is equal to this site or not. So in this case, the answer is no, and therefore I know that my query point is not a member of S. This is an algorithm for answering a query. And the whole point is that this took much less time than it would have taken to compare the query point Q against every single site in S, because that would have taken linear time. But now we only spend time proportional to the number of levels in the tree. But how many levels are there? Well, if we're lucky, then the number of nodes in each level of the tree is twice as much as the number of nodes in the previous level, because every node splits the plane into two halves. Then that means that the number of levels in the tree is really the number of times we can halve our set of sites before we have only one site left. And well, the number of times you can do that is exactly the logarithm base 2 of the number of sites that we begin with. And when this is the case, we also say that the tree is balanced.
So now let's have a look at the problem we started with, range queries. How does a KD tree help with answering range queries? Well, the query algorithm is relatively straightforward. Again, we start with the root of the tree and compare that node to our query rectangle. Now there are three possibilities. One option is that the blue query rectangle completely contains the black region of the node. Another option is that the query rectangle is completely disjoint from the region of the node. And the last option is that the query rectangle intersects the region of the node and might even be fully contained in it. So now let's look at an example. So we start at the root, which is the entire plane. So therefore this is case 3. This node contains our rectangle, so we'll have to go both left and right. Now let's look to the left of L1. We have two regions, the region above L2 and below L2. Well, it turns out the region above L2 is completely outside of our query rectangle, so that is case number 2. So we know that all the sites in here, none of them are contained in our query, and we can safely discard that region. But all the other 3 regions, we have to continue our search in. This region over here intersects our query rectangle, so that's case 3. So we have to go into both subregions. Now, both regions to the left and right of L6 intersect our query rectangle, so we have to continue and check both of them. And the regions to the left and to the right of L7 also both intersect our query rectangle, so we need to check both of them. Now the region to the left of L10 over here is completely outside of the query rectangle, so that's case number 2, and we can safely discard it. But the region above L10 intersects the query rectangle, so we need to continue and check it. The region above L11 as well as the region below L11 both intersect the query rectangle, so we need to check both. For L12, the region above it does not intersect the query rectangle, so we can discard it. But the region below it intersects the rectangle, so we need to continue and check it. Similarly for L13, so the region above L13 does not intersect the rectangle, but below it does. The region above L14 is completely contained in our query rectangle, so that is case 1 over here. So we know that the entire region and all sites in it are contained in the query rectangle. In our case, it's just one site, but in general it could be more. The region below L14 intersects the query rectangle, so we need to continue to check it. The region above L15 intersects the query rectangle, so we need to check it. But the region below L15 lies completely outside the query rectangle, so we don't need to check it. Now for every node on the bottom level that we visit, we need to continue and check whether it's contained in the query rectangle or not. These guys we don't visit. This is the first one we visit. So this one is above L10, which is this one here. It's kind of hidden underneath there, but it's not inside our query rectangle. This one we don't check. This one is above L11. It's also hidden underneath there, so it's not in our query rectangle. This one is below L11, and indeed that's this one, and it's contained inside the rectangle. So this one is contained in our query. This one over here is below L12, which is that one that's not inside our query rectangle. This one is below L13, that's that one not inside our query rectangle. This one, well, this one is the one contained in L14, but we already know that all the sites inside it are in our query, so we don't need to check it again. This one is below L14, and that's outside of the query rectangle. And this one over here is above L15, which is indeed in our query rectangle. So we found our 3 point sites that are contained inside the query rectangle using the KD tree.
So how long does this query algorithm actually take? Well, it turns out that it never takes more time than the square root of the number of sites in our set S that we started with. And this is a bit of a more complicated proof, so I'm not going to go through all the details here, but I hope to give you at least a bit of an idea of why this is the case. So the proof consists of 2 steps. The first step is to argue that the amount of time we spend is actually related to the number of leaf cells that are intersected by a query rectangle. And then the second step is to argue that this number is actually square root of n. So for the first step, let's consider a query rectangle. Clearly, every leaf cell which is intersected by the query rectangle must be visited by the algorithm, because we need to check whether the site in that cell is inside or outside this rectangle. More importantly, any other leaf cell does not need to be visited by the algorithm, because any leaf cell that's outside the query rectangle will never need to test whether the site is inside or outside our query range, because the whole region of that leaf cell is outside our query range. So we were in case 2 of the algorithm. And similarly, any leaf cell that's completely contained in the query rectangle will also never be visited by the algorithm, because we already know that any sites inside such a leaf cell are contained in the query range, so we don't need to check it. So this is why the time it takes to perform a query depends on the number of leaf cells intersected by our query range. And in fact, we can make a similar argument about the number of interior nodes of the KD tree that are visited by the algorithm as well. Alright, so for the second part of the proof, we now need to show that the number of leaf cells that are intersected by any query rectangle can never be more than the order of square root of n. So why is that the case? Well, first I observed that the number of cells intersected by a rectangle is never more than 4 times the number of cells that can be intersected by a single horizontal or vertical line. Because, well, I can draw 4 lines for the 4 edges of my rectangle, and any cells intersected by my rectangle are also intersected by one of those 4 lines. So how many cells can be intersected by a single horizontal or vertical line? Well, in this case, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 cells intersected by one horizontal line. We have roughly 100 points in this point set, so 9 is close to the square root of 100. So let's look at some other lines and see how many cells those intersect. So here's another horizontal line which intersects 1, 2, 3, 4, 5, 6, 7, 8, 9 cells again. So this one intersects 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 cells. Okay, so that's a few more, but still close to square root n. And maybe let's try some vertical lines. This intersects 1, 2, 3, 4, 5, 6, 7, 8 cells. This one intersects 1, 2, 3, 4, 5, 6, 7, 8 cells as well. Maybe try one more. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so all the lines I drew here are intersecting, well, between 8 and 13 cells. And for about 100 points, that's close to square root of n. So now I claim that this is actually going to be true in general for any KD tree. So if I have a KD tree which is balanced, then if I draw any horizontal or vertical line, then it's going to intersect a number of leaf cells in the order of square root n. Now I'm not going to formally prove this claim here, that would go a bit too far, but if you like a challenge, try to prove this for yourself. And as a hint, try arguing about the odd and the even layers of a KD tree. Alright, so that shows that this query algorithm takes an amount of time proportional to the square root of the number of sites in our set S.
So, is that the best we can do? Well, it depends. You know?
Right, so for query algorithms, the situation is a little more complicated than for normal algorithms, because it's not just one thing we're trying to optimize, right? I mean, there's query time.
And the storage, right? So there's a bit of a trade-off. So when you get to use more than linear space, so you can store sort of duplicate, redundant amounts of data, you know, that can help with improving the query time.
Right. Yeah, and in fact, in 1980, John Bentley,
the same who invented the KD tree.
Right. He also invented range trees.
Mm-hmm.
And range trees have faster queries, but they require more storage. That's true.
Right, that's true. And in 1985, Dan Willard, Dan Willard used fractional cascading to speed up the query time from log square n to just log n.
Right. And in fact, log n is the best possible query time we can have, because Ben Orr proved a lower bound for any query that needs to respect n real numbers of log n. In 1883.
Well, the story doesn't end there. So, in 1988, Bernard Chazelle gave a data structure that uses order n space and order log n query time.
So it's the best of both worlds.
Well, kind of, not really, because it cannot use arbitrary real numbers.
And so then, but if it doesn't handle arbitrary real numbers, then the lower bound by Ben Orr doesn't apply.
Exactly, and that's the thing. And for and it's actually harder to compute or to construct lower bounds in those cases, right?
Yeah. So actually, in 2005, there was an improvement over the log n query time. Mm-hmm. This was by Joseph Yaya, Christopher Mortensen, and Kim Shi. And they designed an algorithm for range queries, which has a query time that's faster than log n.
Impressive. Nice. Yeah. Yeah, and then in 2011, Timothy Chen, Kasper Larsen, and Mihai Petrescu even improved on that.
Well, who knows?
Right, who knows? I mean, lower bounds are difficult to prove, and we don't have a lower bound for that setting yet, and so there's still a lot out there for scientists to discover, you know?
Yeah, did I mention that I'm getting a little hungry?
Okay, let's leave it like that for now and go have some dinner.
Right, excellent.
So now that I found all the recipes that I was looking for in time proportional to just the square root of the total number of recipes, it's time to get cooking. And our gumbo is done.
Congratulations, you made it to the end of another Computational Geometry Concepts video. We hope you enjoyed it and learned something.
So today we learned about KD trees and how they can be used to answer range queries efficiently, which allows us to do many queries on the same dataset.
Yeah, and if you want to learn more, we've put links to our sources in the description below, as well as links to other computational geometry concept videos.
Bon appetit!